This is the tutorial to compute fluid properties in SciTool. The dataset used in this tutorial is a synthetic dataset in which a porosity of 60% is assigned to moduli and porosity is decreased exponentially with depth. Sand blocks are added at regular intervals, and within these sand blocks the water saturation is kept constant at 20% and P shale is kept constant at 10%. To the right is the equivalent petrophysical evaluation displayed as volume fractions in a cumulative volume plot. The program computes the physical properties of fluids, that is, the bulk or incompressibility modulus and density. These physical properties of fluids are required to compute analytically rock properties such as P-wave velocity, S-wave velocity, and density that would be obtained if the pore fluids types or saturations were modified. The properties of three fluids are computed: those of the in situ hydrocarbon, the replacement hydrocarbon, and the non-hydrocarbon, which can be brine or water. The data required to compute these properties are the specific gravity of gas, the API density of oil, and the gas-oil ratio, the brine salinity, and the environmental conditions, that is, the pressure and temperature in the well. Let's now start. The properties of the fluids needed to compute moduli and densities are input in these boxes. Here for hydrocarbons, the in situ hydrocarbon, the replacement hydrocarbon. For gas, the specific gravity is input. For dead oil, the API density, and for live oil, the API density, the gas-oil ratio, and the specific gravity of the gas. The non-hydrocarbon fluids are specified in this box, can be brine or water. For brine, the salinity is specified in this box as part per million, and the case of water is the same as having a brine with no salinity. Let's now talk about the pressure and temperature. Pressure, temperature, and brine salinity can be computed as depth variant or depth invariant. When the program is started, they are set to be computed as depth variant properties and parameterized with a constant value at the surface and a depth gradient. This is the box to compute pressure, temperature, and brine salinity. To the left are the parameters to compute these as depth variant properties, and to the right as depth invariant. For the depth variant case, these are parameterized with a constant value at the surface and a gradient of depth. This is done for the pressure, temperature, and brine salinity, and this can be QC'd with the depth variant environment plot. So these are the pressure, temperature, and salinity computed as a function of depth using these parameters. We can also QC the fluid properties that would be obtained using the conditions specified above. Here we have the bulk modulus of the brine, the in situ gas, and the replacement gas. In this case, since the in situ gas and the replacement gas have the same properties, we only see one line. Here is the values of density for the brine and the gas and the velocity. We can also compute these properties as constants. Let's say that we want to use a pressure of 30 megapascals. We type it here and we see that this is equivalent to a pressure of 30 megapascals at the surface and a gradient of 0 megapascals per meter. Let's do here 55 degrees centigrades, and finally let's keep the salinity at 30,000 parts per million. We can again QC the depth variant environment. In this case we set it as constant, 30 megapascals, 55 degrees centigrades, and 30,000 parts per million. And we can also QC the fluid properties. Let's now talk about the bulk modulus and density of the in situ hydrocarbon, the replacement hydrocarbon, and the non-hydrocarbon, whether brine or water. Pressure, temperature, brine salinity, and the hydrocarbon's composition, expressed as the specific gravity of gas, the API density of oil, and the gas-oil ratio, are used to compute the bulk modulus and density of the fluids. There are three possible ways to compute and QC the fluid properties. The first one is to use the depth variant environment the way that we were doing it before. For QC, we can select the depth point, and this is going to populate the QC window with the properties for the in situ hydrocarbon, the replacement hydrocarbon, and either brine or water. The second possibility is to make properties constant for all depths, and finally we can type in the moduli and density of the fluids. Once we're satisfied with the properties computed, we can push the save button and the values are going to be saved for subsequent processes. Let's now illustrate in the program these 3 points. We had mentioned that we can use a depth variant environment. This is the pressure, temperature, and salinity obtained with these parameters. We can select a depth, and the physical properties of the fluids at this depth are tabulated. Now let's say that we would like to use the bulk modulus and density at a depth of 5,000 meters for the whole well. So we select here 5,000 meters and push the button set values as depth invariant. When we do this, we can go back and display the depth variant environment. This is now a constant, and also the fluid properties will be the constant tabulated in the physical properties of fluids table. We also mentioned that we can type in the values. Let's say that we have lab measurements and we want to use those instead of those computed with the depth variant parameters. You can type here 0.2 or 0.1, and now we can look at the fluid properties, and these are now the properties that were typed in this table. Let's now go over the QC plots. We already covered the fluid properties, that is the bulk moduli, densities, and p-wave velocities of the fluids, and the depth variant environment plot, that is the pressure, temperature, and salinity plots. Let's now go to the QC graphs. Here we're going to make 3D plots of fluids moduli and densities as a function of pressure, temperature, and salinity. We are going to compute 3 3D plots for each one of the fluids. That is 3 plots for the in situ hydrocarbon, for the replacement hydrocarbon, and for the non-hydrocarbon. We're going to illustrate this in the program. So we're going to select here QC plots, execute. This takes a couple of seconds, and it generates 3D plots. In this case, we're seeing temperature and pressure and density. So this would be the density as a function of pressure and temperature. This would be for water and for brine. We can rotate the plot, or we can see any of the faces. The second plot is the bulk modulus of the brine as a function of pressure and temperature. Then velocity of the brine as a function of pressure and temperature. Then the in situ fluid, in this case gas, again as a function of pressure and temperature. The density, and then the velocity. And then we would have the same plots for the replacement fluid. In this case it is the same as the in situ one, so it doesn't change. The last checkbox in the plot box is the rock properties checkbox. When this is selected, we are prompted for a couple of parameters. SW is the water saturation to use in the fluid substitution. A value of -1 indicates the in situ water saturation. Matrix is the bulk modulus of the rock in which the water saturation is going to take place. That is where the target or pay flags are. This can be typed or selected as a lithology. Let's do a QC plot. In this case, the in situ fluid and the replacement fluid are the same, and the water saturation is the in situ water saturation, so no changes would be expected. Let's evaluate 50% water saturation. This is how the rocks would look if we had gas as the in situ fluid and the replacement fluid with a 50% water saturation. Let's see how this would look if the reservoir was saturated with brine. So changes are seen in the density and the velocity, especially up shallow where the porosities are high. Let's now change the replacement fluid. So we're going to remove gas from the reservoir and insert live oil, keeping the water saturation the same as the in situ water saturation. These are the resultant rock properties. Let's now again fill with brine the reservoir. And that's how the reservoir would look if it was brine saturated. Two boxes remain to be explained in the fluids analysis program. In the fluids mixing law box, it is specified whether the fluids are mixed homogeneously, in which case Wood's equation is used, or otherwise Ambry's equation is used. An exponent of 1 in Ambry's equation is equivalent to having patchy saturation. In the display units box, it is specified whether fluids are in metric or in English. Selecting English, the pressure is input in psi, temperature in degrees Fahrenheit, bulk modulus in kilo psi, and p-wave velocity in kilofeet per second. The displays are also done in these units. Here, depth is in kilofeet, velocities in kilofeet per second, and impedances in kilofeet per second, grams per cc. This concludes the tutorial on the fluids analysis program. In coming tutorials, we're going to explain how to use these results to do fluid substitution at well log resolution and at seismic resolution. Thank you.